All right, hello everyone. Welcome back to Physical Geology 1403 for your last lecture. The time has come. Please hold all applause and or tears until the very end. All right, I don't know if I can keep it together if you don't. All right. This is the last actual lecture, but for my in-person students, we will be having our second day of class this week because I am required to hold a class, and that's going to be our class movie day. So normal time, be here at 9:30 on Wednesday, but we're going to watch 2012. That's the winner of the movie vote, okay? For any of my online students that would like to participate in that extra credit opportunity, you can watch the movie on your own and complete the extra credit assignment as well, just like everyone else here. I can't broadcast the movie due to copyright restriction. I cannot film a movie being played. So you will have to source the movie yourself. I'm just going to use one of my personal streaming services to play it, one that I pay for, so there's not any copyright issue with that, but there would be if I was then streaming it to you. Let's see. Today is lecture 13, your last lecture, but also the final exam review. So I hope you came prepared with questions. So your final exam is going to cover everything in the class. It's cumulative, as is the nature of most final exams, okay? So everything from Module 1 through what we are learning today. All right, so just bear that in mind. As we go through that review session, after I am done with this lecture, just peruse your notes. Several little students emailed me after the exam one because I gave the feedback. Someone said, how can I do better in future exams? The feedback I gave was your notes should be your best friend, right? Really work on making your notes more robust, more filled out, and asking your questions to me based off your notes. And then I heard back from them after the second exam, and they said, thank you, that was actually really good advice. I was like, oh, this system works, good. Okay, so really, I just really want to push home how important it is to have good, solid notes to succeed in this class. And honestly, the good note skills that you develop or continue developing in my class will only help you more in future education endeavors and careers in general. Okay, any career, there isn't a single career that would get hurt by strong note-taking skills. Okay, it could only help. What else? Before we jump into the lesson, any interesting notes or topics or current events that anyone wants to bring up? Has anything occurred this weekend that might be of particular note? Oh, come on, it's the elephant in the room. Someone bring it up. Yeah, how about our war? On Saturday, the United States and Israel conducted a joint military operation to kill the leader of Iran and many of his top staff. A very, very bold, very risky venture. So I think that it's helped me actually get more of a read on Trump. In his first presidency, Trump was, compared to now anyway, pretty mild. You know, he was willing to talk. He was willing to, be a diplomat to an extent. This presidency, we're a year in, and clearly he has decided, nah, heck with that. I didn't get anything done that time, at least not all the stuff I wanted to. I'm going in guns blazing to get the things done that I think need to get done. Screw Congress, screw the UN, screw everyone else except what he wants to get done. What my personal opinions are on the matter of Iran and the way that their country is run, I will keep to myself. That's not something that I should probably put out on YouTube as an educator. What I will say, though, is that this action has, for Iran, thrown them into a state of turmoil. They're more or less in a state of revolution right now on both sides. The Ayatollah Khamenei had a whole lot of support. He also had a whole lot of dissidents. So things are pretty up in the air over there, and we don't know where politically it's going to land. They could come out of this with a democracy, an actual democracy. They could come out of this with somebody worse. Historically speaking, when you remove a tyrant, it doesn't always end up with the best of results. I mean, we have a few Hitlers and other leaders in our history to demonstrate that, right? So we'll see what happens. We'll see what comes out of this. As far as the United States is concerned, it doesn't cast us in a very good picture. Within a 6-month period, the United States has moved militarily to remove the leaders of countries that are a threat to us and our way of life. Now, it sounds like something we have the right to do until you remember that we are part of an international community. We are a member of a group called the United Nations. Matter of fact, a leading member, a very key member, and we've basically just flaunted United Nations protocol to do both of those things. The first one, yes, people died, but the objective was capture the president and put him on trial for crimes. International community was in uproar about it, but they were like, okay, he's going to trial. Law is being served. For this, we just bombed him. So I think that the international fallout from this one is going to be far more substantial. I think that there's probably going to be some outcry from the United Nations, and I don't know what that's going to be yet. Certainly doesn't help those of us that are trying to improve the United States international relations, though, because that's a big part of what I'm trying to do with my career. And it unfortunately sets a precedent for the other members of the UN that have their own enemies to think that they can do such things as well. If the US can get away with it, well, can't we? Especially if it's someone that the US disagrees with ideologically as well. There's a whole bunch of stuff that can come out of this that could be not so great for us. However good the short-term benefits are, I definitely think that there are some long-term issues that can come out of this. So we'll see. Time will tell. It's still only a few days old. The war still rages, and actually it's only gotten bigger. Several other Middle Eastern countries have joined the conflict at this point on either side. Yeah, Pakistan is not very happy with us. Our embassy in Karachi got invaded. I think several embassies have been evacuated. U.S. embassies out in the Middle East have been evacuated at this point. Pakistan also declared war on Afghanistan. Do you guys see that? No? Yeah. They've always been kind of at each other, but I guess they formalized it. So the whole Middle Eastern region is a little bit in an uproar right now. More than it was before, anyway. I don't remember if it was this class or not, but a few weeks ago, the subject of international conflict actually came up. And somebody asked me where I thought the next war was going to start. Do you remember which class asked me? Was that this class? It may have been the other class. This was like 3 or 4 weeks ago. And I said it's probably going to be Israel and Iran. And here we are. So I don't know how long it'll go, but it's definitely some kind of war. Luckily, not as bad as it could have been, because taking out so much of Iranian military infrastructure at the top, like they describe it as cutting the head off a snake, and that's literally what they did. They killed most of the top brass. So each individual unit commander is now kind of doing the last thing that they were told to do. And so there are Iranian military bases shooting missiles at other countries because the last order they were given was, hey, if we get killed, your specific mission is to target this location over here that would be a threat to Iran. So top brass gets killed, and each one of these individual military leaders is doing the last order they were given, and it's causing even more chaos because no one is responding to any single person giving orders anymore. So again, we'll see where it ends up. But yeah, that was the big thing this weekend. Fun times. Anything else? The lab exam opened last week. Yes. Has everyone taken it? No? You can take it today, by the way, okay? I do have the physical sets that my in-person students can take it with. You can take it in here, you can take it in the hallway, you can come back later today and take it. Today is one of my homework days for my PhD, so I will probably be here until 8 or 9 in the evening. So please feel free to say, hey, I've got some free time, can I swing by the classroom? Yeah, sure, you can spend as much time here as you want. I'll just leave the door open and give you a lab set, okay? You let me know, and we can make it happen. But you absolutely have to take the lab exam soon, because pretty much everyone in every single one of my classes has had to lean upon my flexibility at some point this term, with my flexibility with due dates, okay? Everyone has had to, and I'm happy to be flexible, but the one date I cannot change is the end of the term. I can, and often do, allow you to take more time on assignments up to a certain extent, but the furthest that I am physically capable of going is this Thursday. The term ends this Thursday. I come in on Friday, and I turn in final grades, okay? I cannot push the end of the term. That's a school thing. I can push the due date for lab 1 a week or 2 weeks or all the way to the end, but I cannot change the end. So please turn in everything by this Thursday at midnight, okay? Because I walk in that office 9 o'clock on Friday morning, I close everything, and I calculate final grades, and when I reopen it, what you will see there is going to be your final grade. By the way, this includes all extra credit things. For movie, for notes especially, please get those notes in. You don't get extra credit if you didn't turn in the notes. Make sure everything is turned in. Don't fall asleep don't count on taking your exam that night before. You will fall asleep and you will not complete it or even start it, and then you'll wake up and realize that the course is closed. Okay? Do you have a question?
Yeah. How many questions is the final exam?
Final exam is 45 questions on it, and you have the normal 500-minute time. Okay? That's more than 10 minutes per question. Okay? We'll talk more about the final exam here at the end when we start our review session. But any other things we should discuss or any other questions you have before we jump into the lecture? No? All right. Let's begin. Today we're talking about crustal deformation, a subject we've already discussed a little bit about, in particular when we learned about metamorphism, and mountain building, which is the result of crustal deformation, okay? So what are mountains? When I say the word mountain, you think You think of a mountain range? Fair. That's kind of like me saying what is salt, and you say when something is salty. That's kind of answering the question with the language of the question, right? But what are mountains? And don't worry about how simple your answers are. Kindergarten answers work just fine. Okay, so they are made out of rocks. Sure. Now use words. Ivan likes communicating in sign language. A tall pile of rocks. Okay. What else? Huh? Okay, well now we're talking about how mountains are formed. I'm not quite there yet. A bunch of rocks that have piled high on top of each other? Is that what I'm hearing? So if I took a whole bunch of boulders and I dumped them on top of each other, I could make a mountain? Can we agree that's not quite right, but you don't know how to describe it otherwise? Is that where we're all at? All right, that's fair. That's a fair place to be. We haven't discussed it more than just talking about mountains as generalizations. So that's a fair place to start for today. All right? Mountains, just like you were talking about here, are where plates crash into each other and land, continental mass, is uplifted. Not always continental, it could be oceanic, but I'll describe the different ways that this happens, okay? So, crust is uplifted, okay, over the rest of the land around it, over the rest of the crust around it. Gains in elevation, okay? That's the term, though, uplifted. Now, the nature of mountains, how they form, how quickly they form, this is all a product of the materials in question. You've learned a lot about the different materials here on our planet, right? You've learned a lot about their properties, melting rates, metamorphism parameters, all of these things. All of that comes together to determine how that material responds to stresses. So when you increase the pressure, like you do in a tectonic collision, different materials are going to respond in different ways. You are going to have metamorphism as a consequence here, because we are introducing both heat and pressure. You are going to have crust that gets shoved up and crust that gets shoved down. Okay? Mountains go even further down underground than they do to go up. The rocks that get shoved up have to fight gravity. The rocks that get shoved down have to fight the pressure, the interior pressure of the Earth. Generally, you get a little more on the underground than you do on the top, especially when a mountain gets older, because there's weathering on the top part and there isn't any on the bottom, right? So over time, what's underneath generally is bigger than what's on top. To an extent, I'll talk about that right at the end of the lecture today. Okay? At a certain point, that stops being true. So there are a couple of different types of deformation, which, remember, we learned this in metamorphism, that word deformation. That is any change in a body of rock. Okay? There are a couple of different types of deformation that form as a result of stress. The three types of stress are compression, where you're shoving stuff together, tension, where you're pulling things apart, and shear, where you have unequal forces of stress. Okay? So shear is the type of force that's responsible for creating faults, for example. Okay? If I had a block of Play-Doh in my hand and I just pushed it like this from both sides, okay, I only have one hand, so imagine there's another hand right there holding the Play-Doh, and I pushed it like this, made compressional stress, it would deform up and down, right? If I were to take that and pull on that block of Play-Doh, it would thin out in the middle. But if I were to hold that Play-Doh in both hands, like so, and push my right hand forward and pull my left hand back and make shear stress, what's going to happen? My Play-Doh is going to crack and break, and I'm going to end up with two pieces of Play-Doh. Shear stress is what's responsible for making those faults we discussed last week. Okay? So there are a couple of different ways that materials can respond to these stresses. There is elastic deformation, if my slides want to catch up here. There we go. All right. So elastic deformation is when, just like that rubber band that we talked about last week, you are adding stress, energy to a material. And then it's going to, after it reaches a certain threshold, return to that original shape. That is elastic deformation. So something moves and moves and moves, and then the stress is released and it returns to its original shape. Elastic deformation. It has a flowing threshold, the amount of energy that it needs before it'll start to flow, to move. And then at some point it will break. And when it breaks and that stress is released, it generally will go back to its original or near to its original position. Okay? Then we have brittle deformation. With brittle deformation, once you have your energy reach that certain threshold, instead of snapping back to its original position, it's going to break. It's going to shatter. It's going to make a lot more pieces as a result. And so you go from one unit to a whole bunch of units, just like this poor guy's window here. We've all had days like that, right? Heck, maybe you've had days like that in my class. Hopefully not. I sure have days like that. So that's brittle deformation. Once you hit that pressure, that stress threshold, something is just broken. Okay. Then you have ductile deformation. Ductile deformation means things can mold, they can change, they can take on a new shape and retain it as a result of this pressure that they're put under. Like Play-Doh. I've used Play-Doh as an example a bunch in my class. You can make a whole bunch of things out of Play-Doh. You can give Play-Doh a whole bunch of different shapes, and it will retain that shape until what? Until another force is exerted on it. Okay? That's an example of ductile deformation. So what factors influence what type of deformation we will see? Temperature is a major factor here. Remember, when we were talking about metamorphism, what did we learn that temperature does to a material? What does temperature do to a material? Provides it with energy, and that energy does what? It's giving energy, and the energy is doing what in particular to the atoms inside of it? Use your words. Yeah, it's making them shake, vibrate faster. All atoms are constantly vibrating, right? Any atom that has energy vibrates. Even the solitary atoms of hydrogen out in the void of space possess enough energy that they vibrate a little bit. Do you know what we call it when you remove enough energy from a system that your atoms cease to vibrate whatsoever? What do we call that temperature? Have you heard of this? Absolute zero. Even space is not at absolute zero. The atoms out there still vibrate. Okay? So, all atoms are vibrating, and when you add temperature to something, they vibrate a little faster, and a little faster, and a little faster. Now, if you add too much temperature, they start vibrating apart from each other, and we call that the melting point. But if you give it enough energy that they vibrate faster, but not to the point where they melt, that's when we're in the zone of metamorphism, right? Okay. So temperature plays a big role in how my material is going to respond to stress. If I have a cold material, if I had a cold chocolate bar and I applied some stress, what's it going to do? Break, snap. It'll behave brittly, deform brittly. If my chocolate bar is warm and I bend it, what's it going to do? It's going to bend, it's going to flex. It will behave ductily. Okay? Temperature plays a big role here. Then there is your confining pressure. Remember, confining pressure is the equal forces of pressure given upon a particular area. Now, there's there's the other form, okay, the other type, differential stress. That's the unequal forces, okay? So when you have like a collision, you will get that. But just passively underground in a given area without any tectonic collision, you're going to get confining pressure. Okay? That plays a role in this as well. Then the materials that you have, like I was just talking about, all those materials have different properties. Those properties are going to determine things like how much temperature do I need before I behave ductily instead of brittly, right? So, let me give you an actual real-world example to think about here. Have you ever heard of something called a salt dome? No? Not surprising. Okay, salt domes are big in geology. They're big in petroleum science. Unless your dad happened to be a petroleum scientist, you probably wouldn't have heard of this. Or your mom. Moms are petroleum scientists as well. Okay? So, what happens is you get a thick layer of salt underground. Now, under what circumstances would I have a thick layer of salt anywhere? Think logically about this. For me to have a thick layer of salt underground, at one point, it must have been a thick layer of salt at the surface, right? How might I get a layer of salt on the surface? Seawater, yes. And then what happens? It evaporated. Bingo. Well done. Okay, salt is one of those evaporant minerals that we've talked about, okay? So what happened here? An ancient ancestor of the Gulf of Mexico got cut off from the rest of the ocean. So we have this big old inland sea that's been cut off from new sources of water. And as the temperatures increase, the salt water starts to evaporate, leaving behind the salt, because salt can't evaporate in the water. The water evaporates, leaving the salt behind, and so you get thick layers of salt in this part of the world. Okay? It's not unique here. They occur other places as well. But the layers of rock underneath the Gulf of Mexico are filled with salt. Okay? Tons and tons of salt. Very thick layers of salt, hundreds of feet thick. Now, sediment got deposited on top of that salt, and eventually the connection to the ocean opened up back in, and we get the Gulf of Mexico again, okay, or the Gulf of Mexico as we have it now. But deep underground are these layers of salt. These layers of salt are underneath the layers of rock that would later on become oil-producing and oil-bearing layers of rock. Let me tell you a little bit something about salt. Salt is extremely ductile. It does not take much to make salt behave ductilely instead of brittly. So deep underground, under all that confining pressure and heat, it's going to flow. Not like a liquid, but it's a very malleable, very ductile solid. So this salt finds some weakness in the layers of rock above it. Let's call that shale. This is shale right there, okay, that brown layer. It finds maybe a fault surface or some thinner zone, and it breaks up through that zone of weakness and pushes its way upward. Why? Because it's under pressure and it's trying to get to a zone of lower pressure. So it's going to keep pushing its way up through brittle layers of rock. Brittle shale, broke through it. Brittle sandstone, broke through it. But then it reached this layer. This looks like maybe a shaly limestone. Also also ductile. Behaves more ductilely than it does brittly. So it's going to more or less act as a cap on top of that salt, and this salt is going to essentially balloon out underneath of it and make this structure that we call a salt dome. Now, why is this relevant to the oil industry? Salt behaves ductilely and makes this. As it pushes its way upward, it makes this top layer push upward as well, creating a zone of lower pressure around the top of my salt dome. What else wants to be under lower pressure? All the liquids down there, including oil. So if this layer of sandstone has oil in it, you know where all that oil is going to go? The zone of lowest pressure it can find, around the edge of my salt dome. So in the Gulf of Mexico and here in Texas, where we have hundreds of salt domes, every time we find one, everyone gets excited. And they're like, new oil deposits, practically guaranteed. Why? Because the oil will pool around here where there's a zone of less pressure. So we'll just find the salt dome. We'll drill our little straws down there and pull it out. Now, this usually works out fine, but you have to be very, 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 very careful with this process. Why? Well, salt works great until you introduce one very common, very easily introducible factor. Water. What does salt do in the presence of water? It dissolves. So if you do anything that accidentally introduces water to that salt dome, it starts to dissolve away, and there goes your oil deposit. Okay? This has been known to happen. As a matter of fact, if any of you ever take a trip down Farm to Market Road 1053, going down south, you're going to reach a point where you're driving down the road, and then all of a sudden the road will kind of veer off to the left, kind of skirt around this big hole in the ground, and then return back on course. That big hole in the ground is where, deeper underground, a salt dome used to be. But this oil company, I feel like I heard it was a very small company, like a startup. Very unfortunate for them. But they drilled down to access the oil next to the salt dome, but they didn't seal their hole well enough, and the groundwater seeped its way down there and dissolved the salt dome. Now, as all that salt gets washed away, it leaves empty space. And what happens to empty space underground? The top of the ground collapses into it. So now there's a giant sinkhole out there, and every now and then, every 10 years or so, they have to relocate FM 1053 a little more to the left of that dome, where that dome used to be, because it's still sinking into the ground to make up for the space that's being lost. Okay? So, you just got to be real careful with stuff like that. Always good things to, it's a good idea to think about this sort of thing. Okay. So let's talk about some other ductile deformation structures we can see. I told you previously, when we learned about metamorphic rocks, that when you apply differential stress to a layer of rock, it's going to behave how? It's going to, what do we call this? Fold. Good. Okay. These are folds. Well, as it turns out, we have names for upfolds and downfolds. An upfold, or convex, is called an anticline. Anticline. The downfold, or concave one, makes a trough. We call those a syncline. Okay? So, anticline, syncline. And we will often find them in pairs, like this. Anticline-syncline pair. Okay? Now, that's what we call the actual fold itself, but there's another dimension here, okay? So there's the dimension of two-dimensional plane that gets folded up or down, sure. But we live in a three-dimensional world. Actually, 4 dimensions if you include time, but we're not including time right now, so knock it off, okay? So, 3 dimensions. This is our other dimension, okay? Like this. We call this plunge, okay? So I start with an originally horizontal layer. It gets folded, and then maybe that same tectonic force that folded it, maybe a later force, causes it to plunge. Plunge is a direction, okay? So I can say the anticline is folded and it is plunging to the north-northwest. And that tells another geologist exactly what I'm looking at. Okay? This right here, what you're looking at here, is either an anticline or a syncline that is plunging. How do I know what direction it's plunging in? Any guesses? This way? Or that way? A or B? A? Who agrees with A? Who wants to go with Jasmine on this one? Who wants to say B? Okay, it's A. How do I know that? Because the layers are disappearing under the ground that way. Think about, if I took this anticline, plunged it that way, and then drew a line, a straight line on this horizontal plane to show the ground surface, what would I see? This arch, this fold, disappears into the ground. That's exactly what you're looking at here. It is plunging that direction. Good. Now, how do I know if this is an anticline or a syncline? Somebody tell me. Any ideas? Huh? Sorry, say that louder. It can't be both. It's either or. Sometimes we see them next to each other, but this is one feature. Is it a trough or an arch? Why? I mean, what you're looking at is it sliced down the middle, okay? What you're looking at is either, I'll get some different colors here. That's orange. I'm not sure how well that'll show up for the camera, but I think that might be the last color I have. No. Haha! What do I have here? That's pink. Pink might not show up great either. Green, purple, I think orange is still probably going to be my best bet, but how dark is it? That'll work. It'll have to. Okay. So let me describe to you what we're looking at here. If we have originally, I'm going to get real inventive with the way that I hold my pens here. All right. So if I have 3 layers of rock that are originally deposited horizontally on top of each other like so, and then they get folded into an anticline, what I'm going to have is that. If they get folded into a syncline, what I'm going to get is, hold on. I'm holding them in a different order in my hand. That. What you are looking at here is what happens when one of these features gets weathered down to ground surface. So you're either looking at where's black? There it is. Black is going to represent my ground surface. You're either looking at that or that. It's either this or this in cross-section. How can you tell which one it would be? How can you tell?
Because the way that the wing goes, if it's the U one, then it'll be around it, it'll be different one. And then if it's the one that looks like an N, that one will have like missing. Does that make sense?
Not entirely sure I'm following.
Oh, it would be the order, no?
Elaborate on what you mean by the order.
Because the one that's like this, it starts, the outer ring is green, and then the center one stays the same, and then it's the pink circle. And the inner circle is green.
Yeah. And each one of these different colors represents what?
A layer.
A layer of rock, and therefore a different period of time. So how can I tell if I'm looking at an anticline or a syncline, especially when it's carved in cross-section like this? I don't know if there was an arch here or if it's troughing underneath the surface here. How can I tell? Look at the ages of the rock. Why? Because thanks to our law of original horizontality, we know that they originally started off here. Now, if it's an arch, if it's an anticline, my youngest sediment, which is at the top right, law of superposition, my youngest sediment at the top is going to be on the outer ring, and my oldest sediment will be the inner rings. Okay? This will be older than that. If it's a syncline, my youngest layers of rock are here in the middle, and my oldest are on the outside. So this would be younger than that. Anticline, outer is older. Syncline, inner is older or younger. Okay, got it? So, younger on the outside, younger on the inside. Now, just looking at a picture, it's impossible for you to tell if that's an anticline or a syncline, unless you were really familiar with the geology of an area, and you can say, oh, I know what that red layer is. Yeah, that red layer is definitely older than this limestone here in the middle, right? You could do that, but otherwise you would need to go and collect samples and figure out which is older. And you can do that by looking at fossils, radiometric dating, things like that. Okay, just a little research is all you would need to figure this out. Okay, really cool geologic concept there. Now let's talk about a few other deformation features. Domes and basins. A dome is what happens when some event occurs that causes layers of rock to kind of bow upward in a local area. What I just described to you as an anticline happens as a linear feature. You just saw it kind of stretch off into the distance there in that former picture. What I'm talking about now for a dome is a very localized event. A very common example of this is a magma chamber rises up, solidifies near the surface, and because it is more resistant to weathering than a lot of the other rock around it, as it has pushed the layers of rock above it upward, the layers of rock that come afterward kind of form on top of this feature. And so you get this sort of, here's our granite here, more resistant to breaking down. The schist that it metamorphosed around it, still also kind of resistant. And so the other layers that come later are on top of it. So we have older in the middle, younger on the outside, just like an anticline, but in a localized region instead of as a linear feature. Okay? Then we have basins. That name sounds familiar, right? We live in one. What is a basin? I've kind of described it to you in the past. But a basin is what you call it when you have a low-lying area. That low-lying area starts to fill in with sediment. So here is my, I'm going to greatly exaggerate this. Imagine, imagine that this is, 400 miles across instead of, that compact. But you get the idea, okay? Now, my basin is going to start filling in with sediment. All that sediment's going to wash down into it and make layers down at the bottom. As time goes on, more sediment washes down into it, makes layers at the bottom. Then more sediment washes down into it, makes layers at the bottom. Eventually, it fills in. We live on top of a filled-in basin. This became filled in with sediment largely during a time period called the Permian, hence why we call it the Permian Basin. Okay? So what we're looking at is this. Does that look familiar? It's a syncline, but not as a linear feature, not a fold in a localized area, just like the dome was. Okay? Pretty much the entire state of Michigan is one big basin as well, by the way. Okay? Here you have Upper Pennsylvanian, which is younger, and on the very outside, Ordovician, way, way older. Okay? Older on the outside, younger on the inside for a basin. Any questions about any of that so far? No? Okay. Let's talk about what happens when rocks deform brittly. When rocks deform brittly, that means that they crack, they break. We have a name for that. It's a fault. I already taught you about 3 types of faults. We learned normal faults, where if this is my fault plane, the hanging wall is moving down as the foot wall is moving up. This tends to make a mountain range on the foot wall because it is moving up relative to the hanging wall. Okay, so you'll get mountains on that side. And this is as a result of tensional stress, the pulling effect. Okay? Same sort of stress as what happens at a divergent plate boundary, happening here along this fault zone. Okay? So you'll get your highlands on your foot wall, and it's because of tensional stress. Then we have a reverse fault, where here is our fault plane, foot wall moving down relative to the hanging wall moving up. We get our highlands on the hanging wall. And this is the result of compressional stress, right? Moving towards each other. One side, the hanging wall, is pushing up on top of the foot wall. Then you learned about strike-slip faults, where we have a vertical fault surface, where one side is moving in one direction and the other side is moving in the other direction. You don't really get any highlands in these. They're just scraping past each other, but these are responsible for most earthquakes. The more consistent earthquakes occur along strike-slip faults typically. Okay? But now I'm going to tell you about a third type of fault. Thrust faults. A thrust fault is a very low angle fault that forms as a result of compressional stress, just like a reverse fault. But there's a big difference here. With a reverse fault, you'll notice that our layers of rock are split off from each other. So these were the same layer of rock, but the fault formed and sliced these layers of rock in half from each other, and now they are on top of each other vertically. Okay, one half got shoved above the other. With a thrust fault, the fault plane forms between layers of rock, which means it's at a much lower angle. So we might have a 45-degree reverse fault. Now we're talking 5, 6, 7-degree reverse fault, or a thrust fault. Okay? 5, 6, maybe even 8-degree thrust fault. Okay? Yeah, I saw that chuckle. Okay? All right, so here we still have a footwall and a hanging wall, though. Okay? So what causes this? Still compressional stress, but this is a far more regional event. Okay? This happens over a much larger scale. The area of the world, or of our continent, I should say, that we call the Rocky Mountains, everything from the Rocky Mountains and west, all of those mountainy sort of features are largely caused by various thrust faulting events that have occurred over the last hundreds of millions of years. Big chunks of crust that were thrust faulted from the west coast out to the east, shoved further and further east. And why was it able to go that far? Because of this low angle. Why might a low angle help? You have an answer? Huh? You thinking? If you guys ever run out of gas in your car, you ever had to push your car? When you push your car and you reach a hill, is it easier or harder? It's harder. Why? It's uphill. Why does that make a difference? It's not that there's more gravity. It's that you are now fighting it. On a flat surface, you can push your car and push it and push it and push it. Gravity has a neutral effect, other than just keeping your car on the ground. But once you reach that hill, you are actively fighting the force of gravity trying to pull that car back down. Far, far easier for a whole bunch of crust to get shoved over a low angle fault than it is to get shoved up a high angle one. And so these don't move very far, but these ones go hundreds of miles given enough time. Okay? And that's why they've created such a major geographic features in the center of our continent by getting shoved by collisions from other tectonic plates on the west coast. Okay? All right, but that brings us to our conversation about mountain building itself. There are several different ways that we can get mountains built as a result of tectonic activities. The word for mountain building, by the way, is orogenesis. Orogenesis. Genesis means the beginning, right? To start something. Orogenesis means making mountains. An orogeny is the event. Orogenesis is the process. Okay? We talk about all the different major North American orogenies in 1404 for any of you that are joining me in that for term 2. Okay. The first type we're going to talk about is called a volcanic island arc. This is what happens when two oceanic plates collide with each other. Two oceanic plates run into each other. When two plates collide, what happens? Subduction. When two ocean plates collide with each other, which one subducts? Why would one be heavier than the other? Aren't they both oceanic plates? Their composition? How would the composition of an oceanic plate change? Not so much metamorphism. Metamorphic rocks do occur in oceanic plates, but igneous rock within the bounds of this class is what we are discussing as being the most relevant type. Any other ideas for why one might be different enough from the other to subduct? Let me ask you this. What logic is there for why an oceanic plate subducts under a continental plate? Do you remember? The oceanic plate is what? It's more, I mean, that's true, but what does that have to tie into? It has to do with the mass per volume.
I mean, they have more,
It has more what?
more weight.
Weight is just what is how we describe mass in the presence of gravity. What do we call the measure of mass per unit volume? That's density. So why do ocean plates subduct under continental plates? They are more dense. Even though they are thinner, they are denser. Their material is denser, and so they subduct under a continental plate. So following that same logic, when two ocean plates collide with each other and one subducts under the other, why would that be the case? It's more dense. Why would it be more dense? It doesn't have to do with water depth. Consider this. When you warm things up, the warmer things are they more or less dense typically? They are less dense. That's why convection works, right? Convection, the rise of heat, wouldn't happen if things weren't dense or weren't less dense in that case. When I cool things off, more or less dense? More dense. These are all ideas that we've discussed many times in this class. Now we're just tying them together, right? So, in light of that, with the reminder that hotter things are less dense and colder things are more dense, why would one oceanic plate subduct under another? Doesn't have to do with the pressure. We're assuming equal forces of pressure. But what does warmer mean? Warmer means less dense. Under what circumstances would one oceanic plate be warmer and another one be colder? Not so much positioning. Nope. The equator has nothing to do with the heat of the crust. Heats up the atmosphere just fine. One last tiny idea to tie this together. Why would one crustal segment be colder than another? Because it's further away from the source and therefore older. Yes, this is it. One oceanic plate will subduct under another because it is denser. Why is it denser? Because it's colder. Why is it colder? It's further from the source because it is older. So, in this situation where you have two plates that collide with each other, the oldest of the two will subduct under the younger and therefore warmer and therefore less dense one. Does that logic make sense? You following along? Yeah? Okay, great. So this is what's going to happen. We get one plate subducting under another. This plate has spent its entire existence underwater. That rock is full of water. That water is going to go down into the mantle with that rock. What's going to happen? This goes all the way back to week 2. What does water do to rock in the mantle? It lowers something. Water chemically lowers the melting point of rock. Do you remember that? It was this weird thing we talked about in week 2 when we discussed igneous activity, right? Yeah, it's one of the 3 ways that you can get magma to come up to the surface, okay? So we get melting of mantle rock down here as the water that gets dragged down through that ocean plate interacts with the mantle, lowers the melting point, okay? That mantle pops up here to the surface and makes a chain of volcanic islands here near the subduction boundary. We call those volcanic island arcs. It's where your Japans come from, okay? Then we have Andean type mountain building events. What happens here? You get your subduction of your oceanic plate under a continental plate. And you know what? The exact same thing happens. Water gets taken down into the mantle, melts the rock. You get plumes of magma that come up to the surface, except this time, instead of mafic magma going up through mafic ocean crust to make mafic islands, you get mafic magma that comes up here and meets felsic crust and starts incorporating that into itself. And Bowen's reaction series starts to happen. And by the time it reaches the surface and starts to make those volcanoes, you've got intermediate and felsic magma. And that's going to make intermediate and felsic mountain ranges. This is where all our coastal mountain ranges come from. The Andes, not the Sierra Nevadas, those are mostly volcanic plutons. Okay, but like the Cascades, right, up in the northwest. Okay, that's where these come from. Okay, then we have accretionary belts. And accretionary belts is what happens when those first two combine. So we have our volcanic island arc that formed out there where one plate subducted under another in the ocean. But eventually, the part of the ocean crust that was subducting runs out, and your volcanic island arc runs into a continent. As the plate that it's sitting on gets subducted underneath the continent, the volcanic island arc gets shoved up on top of it. It gets scraped up onto the edge of this continent. We call these accretionary arcs, okay, or an accretionary belt. And this is what pretty much the whole state of California is made out of. The North American plate has had so many ocean plates subduct underneath of it, and each one of those ocean plates covered in volcanic island arcs. Literally, dozens of volcanic island arcs make up the state of California. And that's why so many geologists live in California, I think, is because not only because of all the earthquake activity, but also they're still trying to untangle all of the geology of California, because it's literally a bunch of islands that have gotten scraped up onto the edge of North America. Okay? And then we have collision belts. Collision belts happen when two plates run into each other. Think India running into Eurasia. What did it make? What was the result of India running into Eurasia? Huh? The subduction ended. Subduction was happening until the two plates ran into each other. When two plates are equally dense, they go up and they go down. They make a mountain range, right? It went up and down. What was the result of India running into Eurasia? What's the very famous mountain range out there? The Himalayas, right? The Himalayan mountain range was made by this process. It is a collision belt. Okay, so those are the different ways that you can get compression force to make mountain belts. Okay. Now, as these mountains go throughout their life cycle, so to speak, they climb up, they climb up, they climb up, but they're also shoving down, 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 down. To go up, you have to fight gravity. To go down, you have to fight pressure. But the forces from either side are causing it to go one or the other way or both. Okay? So my mountain goes up in the atmosphere and down into the mantle. Now there's this thing called isostatic adjustment. I already mentioned this earlier in the term when we learned about glaciers. Remember how I told you about the Great Lakes? How the Great Lakes exist because it's a giant depression in the ground where that massive thick glacier used to sit during that last glacial maximum? Well, that glacier melted away very quickly over the course of 1,000 years, right? And the rocks underneath of it that got shoved down into the mantle, making that empty space, that bowl, are still bouncing back up, which is why the Great Lakes are slowly getting shallower over time. Okay? The same thing happens with mountains. So as my mountain range forms, and mountain ranges are extremely heavy, they are pushing further and further down into the mantle. But as weathering and erosion slowly remove material from the top of my mountain range, as mass is removed, the mantle is going to push up on the bottom of my mountain range, like that memory foam pillow rebounding upward after you remove the bowling ball, right? So it's going to actually push my mountain range further up into the sky. So mountain ranges actually stick around for a lot longer than you would think they would, okay? Because instead of just weathering and erosion taking them back down to ground level, the mantle is also pushing the deeper parts of the mountain up as well. So it extends the lifetime of that mountain range. This is called isostatic adjustment. So by the time you actually do end up with the whole bottom of your mountain range getting shoved up to the surface and your mantle reaching its comfortable point again where it's not adjusting anymore, what you have at the surface is the very, very deep, highly metamorphosed rock. Okay? And our older mountain range expressed this. If you ever go out east, go to the Appalachian mountain range. Beautiful mountains, but they are very, very old. And they are mostly deep, crystallized, metamorphic rock, because that's what's gotten shoved up from deep underground as the younger stuff on the top got weathered away. Okay? Questions about that? Good. Well, that's it, folks. Now we can begin our final exam review. So let me give you some info about that final exam. It's going to be, again, like I said, cumulative. So lectures 1 through 13, which you just finished. It's going to be 45 questions, which sounds like a lot, but your first exam was 40. So it's not much more than that. You have your 500-minute time limit. That means from the moment you push start to the 500 minutes later, that's how long you have. If you push start and then go to work, it's going to submit without you. If you push start and fall asleep, it's probably going to submit without you. Put yourself in the best possible situation to succeed here. Okay? I've given you all the tools that I possibly can for your success. Now it's on you to make sure that you succeed by the situation that you put yourself in. Okay? Have a snack on hand. Have your bottle of water on hand. You can get up in the middle and take a walk if you need to. Just don't lose track of time, right? There's plenty of time to take this. Just put yourself in the most winning situation to do it. No tricky questions here. There are no identification questions, like sample identification questions. That's all on the lab exam. Hopefully you've taken the lab exam. If you have not, take it before you take this, because that one was due last week, okay? Or this weekend, all right? Take the lab exam if you have not yet, but know that I'm not going to ask you to identify any samples on this exam. I do, however, reserve the right to ask you interpretation questions. That absolutely is something that we've discussed in lecture. So I might say, this rock has these properties. What can you interpret about this rock or its history or the environment it formed in by these properties? That's a valid thing I might ask. I'm not asking you to identify it. I'm just asking you to tell me a little bit of its history based on the properties. Okay? That's fair game. Any questions from you about the format of the exam, how it's going to move forward? No? Excuse me. All right, well then let's move on into our exam review. Go ahead and pull out your notes. Make sure that they are good and solid. What I'm going to do for this review so that we don't get a lot of dead air is I'm going to pause it, and then every time a student asks a question, I will unpause it. So what you'll hopefully hear is just question, answer, question, answer, question, answer, instead of all the inevitable dead space between questions. All right, so our first question is about aquifers. There was a question on exam 2 about aquifers and the characteristics of aquifers, and some students were feeling a little Like they didn't understand it quite well. So let's talk about that. The characteristics of aquifers that I taught you about are, first of all, an aquifer is pretty much a trapped quantity of water underground. Okay, it is something you can tap into. It's constantly refilling. It's an aspect of groundwater. Okay, but you can pull water out of it, and more water moves into it. Okay, but the characteristics of an aquifer that make something a good aquifer comes down to two things. Okay, let me draw this out here. Okay, so here we have some grains of sediment. Okay, can you see that okay? Let me zoom in real quick so you can see this a little easier. There we go. Okay, grains of sediment. Between these grains of sediment are empty spaces. Okay, these empty spaces are called porosity. They are pores, and the amount of the pores that are present in there are called porosity. Okay, then there's another thing, how interconnected those pores are. Okay, do those pores connect with each other? That is called permeability. Okay, permeability. If they can communicate with each other, then the fluid can transfer from one pore to another. So it's all well and good for my rock to have a lot of pore space. It can hold a lot of fluid. But if that fluid cannot travel from pore to pore, then I can't pull it out very easily. So, ideally, when you want to have a lot of fluids in a rock, it needs to have a lot of porosity. But if you want to be able to pull those fluids out, you need at least a little bit of permeability. Okay? So in the bounds of that particular question on your exam, what I was getting at is you want a lot of porosity and at least a little bit of permeability there. Okay? You want a lot of capacity to hold fluid and a little bit of ability to pull it out. If you have too much permeability, then that can be a problem, right? Not because you're pulling water out or oil out too fast, but because that's going to end up with a lot of empty spaces underground too fast, and your ground can recompact. So ideally, you would have high porosity and low to moderate amounts of permeability. Okay? Did that answer your question okay? Great. What else? I'll pause this again until I get the next question. Well, I'm not getting any more questions for my in-person students, so we're going to go ahead and end this recording here. I'm just going to say, so that my online students can hear this as well, thank you for making the time for my class, for studying. Thank you for taking this class, and I hope that you finish this out with a far greater understanding of your world and some appreciation for it. Also, I'll put this out there. Let me zoom out real quick, just because that's way too close on me. There's this thing called America's Favorite Teacher, which my wife has compelled me to join. It doesn't start for a couple more weeks, but once it does, it's a voting thing. So the more people that vote, better chance people have of winning. So I might send out a message at some point, even though you're not in the class anymore. If you're in a current class, say, hey, if you don't mind, vote for this. You don't have to. It's kind of whatever. It'd be cool if I won. I'm definitely not going to jump on all over TikTok and tell people to vote for me. I'm not going that deep on it, which means I probably won't win, but just put my hat in the ring. We'll see how it goes. But again, thank you for taking my class. And for those of you that are going to be here on Wednesday, I'll see you then. For those of you in my online class, good luck with the final. Let me know if you have any questions between now and the end of the course. But the final is now open.